Hello everyone, I'm Barnabás Pócos. Today we are going to discuss one of the simplest possible machine learning algorithms, the linear regression. We know that the optimal prediction function when we use the mean squared error risk would be the conditional expectation of y given x. The difficulty is that in practice we don't know the true distribution of x and y. We only have a training data available. I denote this training data as a set of input-output pairs xy, yi, and we have n of these pairs. So the goal of machine learning algorithms will be to use this data set, this set of input-output pairs, and try to create a prediction rule f at n which has as small risk as possible and ideally as close to the base risk as possible. There are many different kinds of regression algorithms, all make very different assumptions, and they have somewhat different goals as well. We will discuss the simplest possible regression algorithm, the linear regression, and later during the semester we will discuss some other regression methods. Here I just listed a few other regression methods that are very important in machine learning, such as the lasso regression, ridge regression, smoothing kernel regression, reproducing kernel Hilbert space-based regressions, such as Gaussian process regression, support vector machine regression. There are regression trees, spline regression, wavelet regression, neural network regression, and so on. As we already discussed, the optimal predictor, f star, is a function that minimizes the risk among all possible functions in the universe. The difficulty is, in practice, we only have a training data. We don't have access to the joint distribution of x and y. But what we can do is that we know that by the law of large numbers, the empirical average converges to the true expectation. That's why the empirical average can be used as an approximation of the expectation of f of x minus y squared. However, if we replace the expectation with the empirical average, then it doesn't make sense anymore to minimize this empirical average among all functions in the universe. You can look at that and indeed see if we minimize this expression among all possible functions, then what we get is a function that will have zero error in the training data, but we don't know what it can predict on unseen data. That can lead to extreme overfitting, where our performance again is very good in the training data, but might make huge error on unseen test data. To overcome this difficulty, people typically assume that from now on we are not going to minimize this so-called empirical risk among all possible functions in the universe. We will restrict ourselves to a function class that I denoted with calligraphic f, and from now on we are just going to minimize the empirical risk among those functions that are in this predefined function family. This framework is called empirical risk minimization. Again, what we do here is that we replace the expectation with an empirical average, and then instead of minimizing the risk function among all possible functions in the universe, we will just minimize the empirical risk among those functions that are in a predefined calligraphic f function set. And again, what we used here is the law of large numbers, which just says that the empirical average of these loss values converges to the true expectation for any given fixed function f. In linear regression, we do empirical risk minimization, but we assume that the function set that we consider in the empirical risk minimization, that function set is a set of linear functions. How this function set looks like? If we assume that x is one-dimensional only, then the set of linear functions are just those functions that have this form. F of x is beta 1 plus beta 2 times x, where beta 1 and beta 2 are the parameters of the function f. We are going to use these linear functions for prediction. So for example, in a training point xj, our prediction is beta 1 plus beta 2 times xj, and this is f of xj, and this is what we use to predict yj. Because it's a prediction, we use the notation hat, so our prediction is y hat j. If the training set consists of these blue dots, then we can visualize linear regression with this figure, where beta 2 is the slope of the linear function and beta 1 is the intercept. The multivariate case is similar but somewhat more complicated. In this case, we have p variables instead of 1. I denote them with x1, x2, and xp. These are all real numbers. And the linear equation is just the linear combination of these p variables. The linear coefficients are denoted with beta 1, beta 2, and so on, beta p. These are all real numbers, and together they form a p-dimensional vector. This linear combination can also be rewritten in this short form, x times beta, where x is just a p-dimensional row vector and beta is a p-dimensional column vector. The training set in this case is n p-dimensional points. These n p-dimensional points can be placed in a matrix A. This matrix A in this case has n row vectors and p column vectors. The j's column is denoted with xj, so xj is a n-dimensional column vector. The prediction in the ith training point is just a linear combination of the ith row of matrix A with the p-dimensional beta vector. That is, the prediction in this point is just a linear combination of these p variables with the coefficients of beta column vector. I can do that for all I, and I can put these y hat I predictions into an n-dimensional column vector y hat. So y hat just contains the predictions in the n training points. Each coordinate of y hat, that is y hat I, is just the linear combination of the ith row vector of matrix A with the p-dimensional column vector beta, and I can just rewrite this product of matrix A with the column vector beta. So matrix A is just these p column vectors. These vectors form an n by p matrix, and beta again is just the p-dimensional column vector. So our goal is to minimize the empirical risk function among all possible linear functions. Here xi is a p-dimensional row vector and yi is a real number. Since function f is a linear function, therefore f of xi is just xi times beta, where again xi is a p-dimensional row vector and beta is a p-dimensional column vector. We want to minimize this empirical risk among all possible linear functions, that is, we need to minimize this in beta. We can also see that this sum can be rewritten as a times beta minus y squared norm, where A is just that n times p matrix that we defined in the previous slide, and y again is just the n-dimensional vector whose ith coordinate is yi. In other words, this is just a minimization problem among p-dimensional vectors, where this A times beta minus y squared norm can be rewritten as this A times beta minus y transposed A times beta minus y. Again, just for reference, A is a n times p dimensional matrix. The rows are denoted by x1, x2, xn, and here I'm showing all the entries of matrix A. Y is just an n-dimensional column vector. So our goal is to minimize this cost function in beta, which is just defined by this equation, where again A is a n times p matrix, beta is a p-dimensional column vector, y is an n-dimensional column vector. The solution of this minimization problem is denoted by beta hat. We know it's a differentiable function. Actually, we can even see that it's a quadratic function in beta. Therefore, if I want to find its global minimum point, I just need to calculate its derivative with respect to beta and solve that equation when this derivative is 0. Since this is a quadratic function, its derivative is very simple. We can even drop this 1 over n term as it doesn't depend on beta, and the derivative is nothing else, just a times beta minus y times the derivative of this expression with respect to beta, which is just a transposed, so the final derivative is a transposed times a times beta minus y, that's 0. We need to solve this linear equation in beta. So we have to solve this equation in beta hat. A transpose A times beta hat equals A transpose y. Since A is a n by p matrix, A transpose A is a p times p matrix. Beta hat again is just a p-dimensional column vector, and A transpose y will be a p times n, that is a p times 1. It's a p-dimensional column vector. This is a linear equation in beta hat. This is what we need to solve. If A transpose A is invertible, then our life is very simple, because we just need to multiply both sides of this equation with the inverse of A transpose A. And then what we have is that beta hat is A transpose A inverse times A transpose y. Our prediction function is f hat. We use subscript n because we had n training points, and I just use this capital L notation to indicate that this is a linear function. So our prediction in this point x is just x times beta hat. Again, this is a linear function. Here, as we already discussed, x is just a p-dimensional row vector. So then the next question is, when is A transpose A invertible? You should remember from linear algebra that full rank squared matrices are invertible. A transpose A is a p times p matrix. We know that when the rank is p, then A transpose A will be invertible. There's a theorem which says that rank A transpose A is the same as rank A times A transpose, and that's the same as rank A. When is A transpose A invertible? When its rank is P. So when rank A is P, then A transpose A will be invertible. In other words, if matrix A has P independent column vectors, then A transpose A will be invertible. What can we do when A transpose A is not invertible? In this case, people usually use some regularization trick. We will discuss them later. Now we are going to discuss the geometric interpretation of linear regression. As we discussed earlier, let X be a p-dimensional row vector. The linear prediction at this point X is just X times beta hat, where beta hat is a p-dimensional column vector. And in the previous slide, we already calculated that
beta hat is A transpose A inverse A transpose Y. X is a p-dimensional row vector, and A is a stack of these row vectors. A is a n times p matrix. So we can calculate the predictions in every point of the training set with the following equation. The prediction in every row of matrix A is A times B hat, where again B hat is this expression. From this it follows that f hat A is in the column space of A, since it's just A times a vector, and A times a vector is just a linear combination of the column vectors of A. So our prediction again is in the column space of matrix A. Even if the true outputs, the n-dimensional y vector, is not in the column space of A, whatever we predict, that has to be in the column space of A. The other observation we can make is if I multiply this difference with A transposed from the left, then what I get is that it will be A transposed A times A transposed A inverse, that cancels each out, times A transpose Y minus A transpose Y, and that's 0. In other words, if I multiply this difference f hat n A minus Y with A transposed from the left, that is A transpose f hat n A minus Y, that will be 0. What it means is that the difference f hat n A minus Y is orthogonal to the column vectors of A. As we already discussed, f hat n A is in the column space of matrix A. It could be anywhere in the shaded area, but we also know that y minus f hat n A has to be orthogonal to the column space of A. What it means is that f hat n A is the orthogonal projection of y to the column space of A. Y is an n-dimensional vector. The column space of matrix A, because we have p column vectors, it's a p-dimensional subspace in this n-dimensional space. So we proved that f hat n A is the orthogonal projection of the n-dimensional y vector onto the linear subspace spanned by the p columns of matrix A. And again, just for reference, I wrote that A is a n times p matrix where x1, x2, xn row vectors are our training points. In the next few slides, I'm showing a Jupyter Python notebook code of linear regression. The code is quite straightforward. First, we create 25 two-dimensional points. This will be our training set. Then we create a matrix with standard Gaussian elements independent from each other. The shape of this matrix is 2 times 25, and then we multiply this matrix with another matrix C, and this C times the previous matrix, that will be our final training set. The size of this training set is 2 times 25. We have 25 two-dimensional points. You can think of these two-dimensional points as one-dimensional input-output pairs, and here I'm just visualizing these two-dimensional points. X-axis is the input, y-axis is the output, and our goal is to fit a linear equation to these points. We set y to be the output, and then we modify x again slightly. We add constant ones, that's sometimes called the bias term, to x, and that will be responsible for the intercept term. And then we create matrix A, which is a 25 times two-dimensional matrix. Beta, as we discussed in the previous slides, will be A transpose A inverse times A transpose times Y. In this case, this beta is just a two-dimensional column vector. Then we plot with blue dots the original training points, and with red, in each training point, we plot A times beta, our predictions. And as you can see, this red curve is the fitted straight line on the training points. For a general matrix A doesn't need to be full rank in this case. The pseudo-inverse of A plus, provides a so-called linear least square solution to a system of linear equations. This linear system of equations is A times beta equals Y, where A is an n times p matrix, beta is a p-dimensional column vector, and Y is an n-dimensional column vector. For general A matrices, this system might not have a solution, but we can always minimize the error A times beta minus Y square norm in beta. The main theorem is as follows. For any beta p-dimensional vector, we have that A times beta minus Y norm is at least as big as A times Z minus Y norm, where Z is the pseudo-inverse of A, that is A plus times Y. Let's see what exactly the pseudo-inverse is. For any matrix A that's m times n dimensional, the pseudo-inverse of A can be defined as A plus will be n times m dimensional, same dimension as its transpose, and the pseudo-inverse will satisfy all of these four properties. A times A plus A is A plus A times A plus is A plus, A times A plus transpose is A times A plus, and finally A plus A transpose is A plus A. You can see when the inverse exists, then the inverse indeed satisfies all of these four properties. That is, for example, A times A inverse A, that's A, or A inverse A inverse, that's A inverse, and so on. For a general matrix A, however, the inverse might not exist. One can prove that the pseudo-inverse A plus always exists and is unique. However, when A has full rank, then A plus has a simple form. When A has linearly independent columns, A is a tall matrix and all of its columns are independent. In this case, A transpose A is invertible, and A plus has this very simple form, is just A transpose A inverse times A transpose. This is called left inverse, since in this case it's easy to say that A plus A, that's A transpose A inverse times A transpose A, that's the identity matrix. When A has linearly independent rows, again the pseudo-inverse in that case is very simple. When A has independent rows, then A is a flat matrix. And in this case, A times A transpose is invertible. And one can prove that A plus has this very simple unique form. A plus is A transpose, A times A transpose inverse. This is called right inverse, since in this case one can easily see that A times A plus, that's A times A transpose A times A transpose inverse, that's the identity matrix.
The pseudo-inverse is important because it can provide a linear least square solution to a system of linear equations such as A times B equals Y, where A can be any n times P matrix. It doesn't even have to be full rank. In general, a vector beta that solves the system A times beta equals Y may not exist. There might be infinite many solutions, or there could be one unique solution. The pseudo-inverse solves this A times beta equals Y problem in a least square sense as follows. One can prove that for any beta p-dimensional vector, the norm of A times beta minus Y is at least always as big or bigger than the norm of A times Z minus Y, where Z is the pseudo-inverse times Y. So Z is that vector that minimizes A times beta minus Y in beta. One can also prove that equality holds in this inequality if and only if beta has this form, A pseudo-inverse times Y, that is Z, plus another vector I minus A plus times A times W, where I is the identity matrix, A plus again is the pseudo-inverse of A, and A is an arbitrary n times P matrix. W is an arbitrary p-dimensional vector. So one can prove that as long as beta has this form, this beta minimizes the norm of A times beta minus Y. And all the solutions have this form. We are not going to prove this, but at least we can easily see if beta has this form, then that beta is indeed an optimal solution. So let beta have this form, then A times beta minus Y is nothing else, just A times beta minus Y, that is A times A plus times Y plus A minus A times A plus A times W minus Y. And we know by the definition of the pseudo-inverse that A minus A times A plus A, that's always the zero matrix. Therefore, what we have is that A times beta minus Y is just A times Z minus Y, so this beta is indeed optimal. The other direction, where we need to prove that all the solutions have this form, that's a bit more tricky, and we are not going to do that. So what we have seen so far, that a pseudo-inverse provides a least square solution to a system of linear equations, A times beta equals Y. In general, this linear system, A times beta equals Y, may not have a solution, may have infinite solutions, or can be just one unique solution. The number of solutions depends on A and Y as well. To have a solution, Y has to be in the column space of A. To have a unique solution, A also has to be full rank. The pseudo-inverse solves this problem in a least square sense, that is, the pseudo-inverse tries to minimize the norm of A times beta minus Y. This minimization problem can have either one or infinite many global optimal solutions. The number of solutions depends only on A. Y is irrelevant in this case. As we already said in the previous slide, all the solutions to this minimization problem can be found in this form. Beta is A plus Y plus identity matrix minus A plus A times W, where W is arbitrary p-dimensional vector.
From this form we can indeed see that this minimization problem has infinite many solutions unless A has full column rank, which would imply that A plus has this form A transpose A inverse times A transpose, and because of that identity matrix minus A plus times A is a zero matrix. So this extra second term in this case is always zero, and the solution is unique, beta equals A plus Y. Interestingly, linear regression can be used to solve nonlinear problems as well. One special case is the polynomial regression. Let x be a real number, beta 0, beta 1, beta 2, and so on, beta m be n plus 1 real numbers. And let's create a polynomial which is just f of x equals beta 0 plus beta 1 times x plus dot 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 beta m times x to the power m. And I can rewrite this polynomial as x times beta, where x is just an m plus 1 dimensional row vector that consists of 1 x squared dot 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 x to the m, and beta is an m plus 1 dimensional column vector. In other words, x contains the polynomial basis functions, the constant 1, the identity function x, then the quadratic function x squared, and so on, finally x to the power m function. And beta vector contains the coefficients of this polynomial. Let's assume that our training set consists of n input-output pairs, x1, y1, x2, y2, and so on, xn, yn, and in this case xi and yi, they are all real numbers. From x1, x2, and so on, xn real numbers, let's create the design matrix A, which contains the basis functions evaluated at x1, x2, and xn. This is a n times n plus 1 dimensional matrix. Now we can use linear regression using this design matrix, and as we calculated in the previous case, the optimal coefficients beta hat is just A transposed A inverse A transposed Y, and this is an n plus 1 dimensional vector. If we want to use this polynomial for prediction, all we have to do is to calculate the prediction function f at n, and this is nothing else, just we calculate the basis functions evaluated at m, we create a row vector from it, and then we multiply this row vector with beta hat column vector from the right, and that will be our prediction. So in other words, the prediction is nothing else, just sum beta j x to the j, where j is going from 0 to m. This is called polynomial regression. One can even generalize this further and replace the polynomial basis functions to any functions, for example to Fourier functions or whatever that person might like. And in this way we can use linear regression to solve nonlinear prediction problems. Let's see how this polynomial regression works in practice. Here we create a noisy sine function where the training set consists of 45 points, and first we create the 45 input numbers. These are all real numbers. Then we calculate a noisy sine function of it. Actually it's sinus 3 times x plus some Gaussian noise. And then we plot our training set. Our goal is to calculate the prediction function at any given point x using this training set. So first we create the 45 dimensional column vector y, and then we create the A design matrix, which will have 45 rows as we have 45 training points, and we will use ninth order polynomials plus the constant. So this design matrix A will have 10 column vectors. Then we calculate the 10-dimensional column vector beta, which is just again A transpose A inverse times A transpose times Y, and then we are done. Then we can plot the original training set, and we can also plot our prediction in the training points. That will be A times beta. I connected our predictions with a straight red line, and you can see that the predictions are actually pretty good even in those points that are not in the training set. So you can see that polynomial regression in certain problems can be a very efficient tool for doing prediction. And the beauty of it is that we only need to solve linear regression on the polynomial basis functions. In the next few slides, we will investigate what is the relationship between least squares linear regression and maximum likelihood estimation. The intuition is that we can also think of linear regression as a generative model where y outputs are generated as some prediction function f star x plus a noise vector epsilon. In linear regression, this prediction function is linear, say x times beta star, where x is a p-dimensional row vector, beta star is a p-dimensional column vector. Epsilon is a Gaussian noise vector with mean 0 and variance sigma squared. In this case, we can say that the conditional distribution of y given x is just a Gaussian distribution with mean x times beta and variance sigma squared. That is, the conditional distribution of y given x has this density function, a Gaussian density function. Now let our training set consist of n input-output pairs where the inputs are p-dimensional row vectors and the outputs are just real numbers. The maximum likelihood estimation is to find that beta that maximizes the probability of y1 and so on yn given x1, xn and the parameters beta and sigma squared. If I want to maximize this density in beta, that beta that maximizes the density is exactly at the same location where that beta is that maximizes the log of this density, because the log is a monotonous increasing function. Now, since all yi is independent from the other y's, we can rewrite this log as the product of n of these terms, yi given x1, x2 and so on xn, and the parameters beta and sigma squared. Moreover, if I want to predict yi, for this prediction I only need to use xi. The other training points are irrelevant, so this probability is exactly the same as the product of yi given xi, beta and sigma squared. And now we are almost done, because we know that all of these probabilities are Gaussian distributions with mean xi times beta and variance sigma squared, so they have this Gaussian distribution. If I want to find a beta that maximizes this expression, I just need to solve this maximization problem, and because the log will cancel the exponential function, our final problem is nothing else, just find that beta that minimizes this sum of squared expression. And if you look at it, it's just a least square linear regression problem. So the least square estimation in linear regression is the same as the maximum likelihood estimation under the Gaussian model in linear regression. In the previous slides, when we calculated beta hat, we always assumed that A transpose A is invertible, because in beta hat we needed to calculate the inverse of A transpose A. What can we do if A transpose A is not invertible. One trick that people do in this case is the so-called regularization trick. So instead of just solving this maximum log likelihood problem that maximizes in beta the log of this probability, we assume a prior distribution on beta, and then instead of a maximum likelihood estimation problem, we solve a so-called maximum a posteriori estimation problem. Quite often people assume that on beta there's a prior Gaussian distribution, that is the density of the prior distribution of beta looks like this. Then it's easy to see that the maximum a posteriori estimation is equivalent to this problem, where in the cost function we have two terms. One is the same term as before, but the other term is plus lambda times squared norm of beta. And you can prove that even if in the previous case A transpose A was not invertible, the new matrix what we will need to invert now will be A transpose A plus lambda times identity, and that A transpose A plus lambda times identity, that's always invertible. So inversion is not a problem anymore. This is called ridge regression, and we will discuss the details of ridge regression later during the semester. So in ridge regression, we used Gaussian distribution as a prior distribution on beta. Sometimes, however, people use Laplace distribution on beta instead of Gaussian distribution, and then our final problem will look like this. Again, in the cost function we will have two terms. One is the same as in the least square estimation problem, plus we have a second term which is just some lambda times the one norm of beta. This problem is called the lasso regression problem. We will discuss some of the most important properties of lasso later during the semester. In this lecture, we have seen how to use the empirical risk to approximate the true risk. Then, as an application of it, we discussed the linear regression problem. We have seen an algorithm for the linear regression problem. We have seen the geometric interpretation of linear regression. We introduced the pseudo-inverse and then discussed how to use the pseudo-inverse to solve the least squares linear regression problem. Then we introduced polynomial regression, which is a nonlinear regression problem that can be solved with linear regression. Then we discussed the differences between least squares regression and maximum likelihood estimation. Then we discussed what to do when the A transpose A matrix in the linear regression problem is not invertible. And then we discussed two regularized linear regression problems, the ridge regression and the lasso regression problems. We will continue from here next time.